Hello to everyone. We are the Group 8, composed by Miguel Valdés Tabernero, Javier Sánchez Gutiérrez, and Iñigo Sancho Fernández. We are going to tell you about the design of a fishing rod, so let's get a more accurate idea of what this work is going to talk about. The goal of this project is to design a fishing rod for seawater, which allows us to fish big species, as for example, swordfish. The model will be simplified. We are going to neglect the fishing bait, the string, the reel, and also the handle. We are just going to take care about the rod. Also, we are going to assume that the rod consists on a continuous cylindrical shape. Then we will need to specify between the solid cylinder and a hollow cylinder, a tube, but that could be later. The main function of the rod is to be able to resist heavy fishing. We have taken as a reference the swordfish, which is one of the most important sport fishing modalities. But when we are talking about swordfish, we have to take into account that we are fishing an animal that its mean weight is about 150 kilograms, and it's particularly aggressive in the fight against the fisherman, so it's not a simple fishing. Hence, the rod must be able to support high bending stresses. So that leads us to the next step. The first requirement, and one of the most important, is the salt and freshwater resistance. Due to the environment of the fishing, the resistance to salt water is required in order to maintain the optimal characteristics of the fishing rod during large periods of time. Also, it's important to consider the fresh water to avoid degradation during cleaning or if it's used in lakes or river. Water corrosion is one of the first problems that must be solved because it can produce failure very easily. Another requirement is the size, the weight, and the shape of the rod. Let's get into the weight first. In order to avoid extra fisherman effort, the weight should be as minimal as possible, but always fulfilling the rest of the requirements. For example, the size. The rod length is a personal preference. A shorter rod provides you more control and maneuverability, more accuracy, but a long handle rod will give you more power for greater casting. The shape, finally, has to be comfortable to be handled, because we don't want damage to fishermen during fishing, especially in heavy fishing. The radius of the rod is limited by the difficulty of manipulation also. The mechanical behavior makes us an idea of the properties. The first one, the stiffness, describes how much force it takes to bend the rod. The stiffer the rod it is, the less flexible. Stiffness depends on the material used to make the rod and the amount of material used. A stiffer rod will help us pulling out a heavy fish, as for example a swordfish. On the other hand, brittleness shows how easily the rod will break. Brittleness and sensitivity tend to be indirectly proportional. Finally, the action describes how much of the rod bends when you put pressure on the tip, and the speed with which the rod will return to its neutral position. It is used to describe the flex point of a rod, and can be slow, medium, fast, or a combination. Other main points are, for example, the recyclability. The rod, as far as possible, has to be reusable, and why not biodegradable in case of some part of the rod ends in the sea. Also, the toxicity. The material for the fishing rod cannot be toxic, in order to avoid an injury produced by its contact with live organisms. And at the end, the economics. The final objective is to sell our fishing rod, so we need to be competitive, not only with the quality, but also with the price. The first step for a material selection case is to identify the function that our material has to fulfill. As we are working with a fishing rod, its function must be able to resist bending stresses that appear during the fishing. As a constraint, we have to realize that the bending stresses in the rod must be lower than the critical bending stress. Also, the rod should stand 150 kilograms, the swordfish, and the safety factor must be higher or equal to 1.3. Also, the rod length is fixed to 5 meters. And as we have said before, eco-friendly and economics are also two main points. Going to the objective, it is needed to maximize the elastic energy storage, to enhance the ability of the rod to return to its original shape, making it easier to fish big species. On the other hand, we need the minimization of the mass, to save as much weight and money as possible. As free variables, we have the material, the rod radius, and the specific shape of the cylinder, bulk or hollow, that it is still not selected. In order to get a good selection, we should start simplifying our case. So we are going to assume that our problem can be modeled as a cantilever beam with a punctual load in one of the extremes. We have worked with the well-known formulas of the small deformation theory that normally cannot be assumed in the case of fishing rod because large deformations are involved. But in this case, for material selections, the formulas are perfectly appropriate and we can obtain the indexes quite well. Moreover, we have selected the tube shapes, the hollow cylinder for the beam, because it gives us higher shape factor for the case of bending than the case of a solid cylinder or bulk, and it helps us to save material. For the material indexes, we are going to obtain two performance equations that then will be maximized or minimized depending on the objectives. The mathematical development can be seen in the report. Here we're going to focus on the result. The first material index, M1, corresponds to the elastic energy storage, or in other words, resilience. And the second material index, M2, corresponds to the minimization of the mass. These two indexes are going to be put into the EduPack test program. In the selected panel, we have to put a behavior against freshwater of excellent, a behavior against saltwater of excellent, and a fracture tolerance of minimum 20 megapascals square root meter to avoid easily fracture. As we can see, we have just some materials left, not all can be selected. Now it's time to put a slope that becomes of the logarithmic equation. The first one is for the first index of resilience is slope of 2, and we just need the down left part, higher flexural strength and lower young modulus. And in the other graph, we just need a slope of 0.66 and also the down left part, lower density and high flexural strength. The materials left are epoxy X-glass fiber composite zero lamina, big IM carbon fiber composite zero lamina, and epoxy carbon fiber composite zero lamina. By using the tool of Test EduPack of Synthesizer, we have selected some materials that are not into the classical ones. We have chosen a sandwich balanced panel composed by two sheets of 0.5 millimeters at its stream and a core of another material. The first one is composed by two sheets of epoxy glass of 0.5 millimeters and a bamboo longitudinal in the core. The second one big in the extremes and epoxy in the core, and the first one big in the extremes and bamboo longitudinal in the core. These materials, as we can see in the images, are similar to the classical and in some aspects are even better. So we have a preliminary selection. As we can see in the table comparison, the mass and the radius are more or less the same in all the materials, near 1 kilogram from the weight and near 1.2 radius in the radius. So we must see the total cost and the minimization and maximization of the indexes. M2 must be maximum in order to the high energy storage, and M1 must be minimum in order to minimize the mass. As we can observe, most materials have its own pros and cons. For example, the epoxy X-glass fiber bamboo is the cheapest one and has a relatively good relation between the indexes, but not the best one. For example, the big I am carbon fiber has the second best indexes, but is by far the most expensive one. So we must see other processes to select which is the basically best one. The processing is going to be a key parameter because some processes can make only simple shapes while others are able to create more complex ones. So the first thing that we have to do is checking which processes are able to fabricate fishing rod. It will have a circular shape made of composites. Then from these processes we have to select the ones that can fabricate discrete parts. Then the ones that can deal with the required thickness. By choosing in the options, we finally obtain centrifugal molding and filament weaving like the final ones. By economical terms, we finally select the filament weaving. This will get new restrictions to the materials that can be showed in the new tables. The product mix is a good parameter that shows the efficiency of the material in order of the indices. As we can see, epoxy X-glass fiber glass bamboo is the first and the best one right now. Finally, it's a good idea to look at the eco-audit profile of each material to see which material is the most eco-friendly. As we can see in the tables, we can compare the energy consumption for each materials, the CO2 footprint generated per each material, and the cost per each material. Analyzing all the results is doubtless that the winner is the category in this category is the synthesized material epoxy X-glass fiber plus bamboo, since by far the most eco-friendly and cheaper solution. Also thinking about taking part into luxury market, we cannot forget that we have competitors, so we have to think in reducing the price as much as possible. For that reason, big IM carbon fiber plus bamboo is not an option. Taking the price into consideration, it is clear that the best option by far is the new material that we have thought about, epoxy X-glass fiber plus bamboo. Also taking into account the eco-audit information. Finally, we have two options, the classical material and the new one created by us. As both options have to be done using the same processes, filament weaving, the same resin, epoxy resin, and continuous fibers, the same facilities and machinery can be used. Therefore, we can still produce in epoxy carbon fiber fishing rods until we develop the way to introduce our new models in the factory and the industry.